Hello, welcome to my channel. Welcome back to my channel rather. And today I will be discussing about a very interesting topic. I hope you all have been very good and keeping good health. So I have been hearing from many of my students and colleagues and friends who work on the field of embedded designing with microcontrollers, and most of them are very hugely dependent on I2C EEPROMs or SPI EEPROMs. Now, I would like to discuss a very interesting topic today. That is, what are the alternatives, or rather, an alternative to using such EEPROMs? Now, these EEPROMs not only add to the cost and complexity of the code, but it also increases some hazard or some risks that I will share in my slides. So let us get started with it. So today's agenda is very simple. Just using I2C EEPROM, like where we use it and what are the use cases. Risks and costs and risk mitigations for that, what are the alternative solutions available, and finally, how do we use the flash, which is just an alternative to using an EEPROM to store the data and retrieval. Now, the first question that arises is that why do we use I2C or SPI EEPROMs? Obviously, to store data. What kind of data? User data, device configuration data. It can be also device identification data. So no matter what kind of data you need to store on I2C EEPROMs, you can always do that with Flash. Now the question is that most of the Flash, which is available for any low cost MCU, they might not be available for access when the code is running from Flash. So these are special MCU functionalities which are available these days, where you can actually access a Flash area and you can actually retrieve data from there. Now, I2C or SPI EEPROMs are very common solution, obviously, to store data, device configuration data, or device ID data. Some even store, like encryption passwords. So the data is like it can be n number of use cases for that. What are the examples? Obviously, examples are 24CXX series, like for example, we have 24C080264, or we also have the 25AA series, which are the SPI series for users. Now, apart from that, there are also other kind of memories available, but no matter whatever memory you use, whether a synchronous communication or maybe asynchronous communication, it always adds on to an external interfacing and cost, and obviously code complexity. So SPI and I2C are both synchronous serial communications. I hope like that's a topic that is beyond discussion of this particular video, but the only thing that I would like to say is that most of the EEPROMs which I use, maybe say around 80 to 90% of the microcontroller based small designs, they are I2C or SPI based. So that can help to store and retrieve data across multiple MCUs. So even that helps you, if you have a multi-master communication wherein like 2-3 masters are taking data from the same EEPROM, so that those use cases can also be taken care of. Obviously not with a single solution, but nevertheless you can add on to the complexity of the system that I'm discussing today. So that's the first thing. Now, when we come to the risks and the costs, so what are the risks? Now, I2C and SPI, both of them require a proper bus timing. Now, what do I mean by bus timing? Suppose if you have a PCB where the bus track lengths are huge, or you have a larger parasitic capacitances. So in those cases, you have to discuss, discuss with your teammates maybe, or maybe you'll have to, look up to the data sheet and calculate the capacitance or the pull-up resistors in order to make the I2C communication going. Similarly for SPI, it is sensitive to speed of the MCU that you're using. Failure of the bus and clock lines will obviously make the data unavailable. So for example, let's say under any circumstance you have the I2C channel not working, or even if you have a bit banging in case if there is a pull-up resistor problem, so the I2C data will fail to be fetched and it can hang your device. So this risk is always there. Also, if you want to add on some additional EEPROM, that will add to the cost as well as the complexity of the PCB, because if you are using SPI slave device, then you will need one pin to pull down the slave. So these are some, costs and risks that you have. And nevertheless, apart from this, you have the complexity of interface logics. There may be some business logics, and there can also be some encryption of the data. So all these things will, it will always add on to the complexity, and it will increase the development time. So what's the solution or alternative that can be done? So if you are using, like me, if you're using, MSP430 or an equivalent MCU, then obviously you have an SRAM or flash area where you can access and store your data. The second thing is you can use the flash memory as a data storage for your own device, as well as for the data which is there for the user. So it doesn't matter, like you can make a memory map design for your project, and you can segregate the memory areas for your own data as well as the device configuration data. The only thing that you need to keep in mind is there are some critical regions of the memory or flash that you should not overwrite. One of them being the bootstrap load of the BSL area, and also the configuration, the calibration configuration constants. If you're using MSP430, then it's the info A area where the calibration constants are there. So if you're using some other MCU, please discuss with your teammates, or like you might want to refer to the datasheet. There are certain device specific data sheets which are available, and they can really tell you that which particular memory area is also not available for access. So if there is a memory protection unit, for example, if you're using an ARM Cortex processor, then there will be an NPU protecting a particular memory area, and there will also be a lock password that or a firmware key that you need to supply, as we'll see in our example. So in our example, I'll just show you a very short demo with MSP430 memory flash access, where we will be doing the same thing which we do with the EEPROM, but very simply at a particular flash memory area. And one more thing that we need to remember is that data in the flash, they are by default, it's not a password, but I have just used the word to make it simple. It's rather a lock key. So whenever you need to write to the flash, you must supply the lock key or the firmware key. And also after a certain interval of writing, you have to lock your flash memory area. That's simply because the flash memory which is there inside the MCU, it has a limited writing exposure time. So this is something that you might want to look into. So just refer to your device datasheet. There is a particular restriction in timing through which the flash is stressed to the higher voltage or the higher programming voltage. So you can't just keep on writing the data and keep the flash on, or the flash writer process on. So you need to like turn it on, write the data, and turn it off. So apart from that, everything is very easy. So if we are just taking into consideration a simple MSP430, you can see over here, let me just turn on the. So here you can see that the RAM is there, which you can use to store your data. But again, remember that the RAM might be flashed out. So if you need to store your data in non-volatile manner, I would recommend you to use the flash or ROM area. Now, if you're using the flash, then obviously there are certain areas where your own code is stored. So it's better not to clash with that area. Otherwise, you might experience some unexpected stack crashes, or although the stack is in the RAM, but there might be some unexpected program terminations or program crashes. So remember to use a memory area which is not colliding with your own text data. So that can be seen by, if you have a look at your map file once your program is compiled in your IDE. So just select a particular memory area from there. Okay, so here it goes. These are the three areas which you can use to store your data: the RAM and the lower flash and the upper flash. So there's nothing called the lower flash or upper flash you will find in the datasheet. I have just referred to them because one flash is the flash part above the vector interrupt table, and the other part of the flash is which contains the vector interrupt table. So you can choose your any area you want to store. This is a very simple example that I have tested on a MSP430 MSP430F5419A microcontroller from Texas Instruments, and it uses the Code Composer Studio, and some part of the code is taken from the Texas Instrument Resource Explorer, which I will show you in this video. So if you're using the CCS from TI, then I would recommend to go into the Resource Explorer and like first go through their example code and then modify. However, the code over here is very simple. We just declare a simple pointer to the flash over here, and this is the memory location that you want to start programming, and then you reference it to the memory area that you want to use. For example, I have used 1800 hex, but you can choose any address according to your own design. And then you can see over here, we simply provide the lock bit. This is the lock, as I was saying, this is the lock password or the lock key. This is the firmware lock key, and after giving the firmware lock key, we erase the flash. So remember, if you're using the SRAM area, you have to erase, or even if you're using the flash area, most of the microcontrollers, the flash supports erasing of the entire flash segment before you write any data into it. So if you're using, for example, segment A, then you have to erase entire segment A and then load data into segment A. So this is something that is a bit tricky when you need to implement it in place of your I2C EEPROM, where you can just keep on writing to the memory area. But I think it's not that challenge as well. You can manage it as compared to the cost, the hardware cost that we have. So we first clear the memory area, and then we enable the long write mode. In the long write mode, we can save any 32-bit data, and after that, after the data is pushed into the memory area, you immediately lock the flash. So once you have written to your memory area, you just dereference it like a pointer, and you're done. So it's that simple. Nothing much great that you have to do into it. Now, what can you do after this, or what are the use cases that might interest you? So the first use case is obviously the OTA, that is over-the-air upgrades. So if you are using a flash MCU where you have access to the flash, you can always update small portions of your code. But again, I would like to tell you, please go through your entire device datasheet and please understand the program flow inside the memory area. It should not happen that you corrupt your own code when you're updating, and not all the microcontrollers support the access to all the memory areas. So one process is OTA that might interest you. It is possible to take critical area backups. So if your flash has some critical data stored into it, so you can always take a backup of the data and store into some other place, whether it be RAM or into some other backup device. That is also possible. You can also take a backup of the run of the RAM, I'm sorry, and some flash areas, as I said, they first need to be set to 0 and then rewritten with the data. So you have to modify your code accordingly. And in the upper part of the flash, you can also store data without setting it 0. So that is something that I've tried and tested. It works. So you can also do that. That's up to you. If you don't want to set it to 0, if you don't want to modify the segment, you can go for that. And as I said, that please keep in mind that there are some sections of your microcontroller, some flash areas which contains calibration data. So if you erase that, you will have to go through a detailed factory programming procedure described in the Texas Instrument website in order to get them back. So it's better to consult the device datasheet, the user guide, and then go into the system. Okay, so now I will just show you a very small demo. So this is the Code Composer Studio code that I used, and if you would like to see where it is available, you can simply go to the Resource Explorer. In the Resource Explorer, you will have on the left side, you will have the software. Inside software, you will find MSP430 wire. Inside it, you will have devices. So I have used 5419A, which is this one. You can choose your own device, whichever you're using. So inside that, you will have flash write 02C. So you can just click over here and just click on import to CCS IDE, and it'll ask for the flavor, and then you can just simply have it inside your Project Explorer. Now coming back to the actual code, that is this one. I have just modified it in this way, just maybe modify the values a bit and tweak them. So I have a MSP430 hardware connected with me. So after you design your code and do whatever changes you want, you just simply click on the debug, or you can directly download your code if it is already a compiled code. So once you download your code, as you can see, it is being downloaded. you can simply run the code and we can see that the actual data is being stored inside the MCU. So we'll wait for the program to be downloaded. Here it is downloaded. And on the right side, I would suggest you to open the memory browser. How do you do that? You go to view and you click on memory browser. So once your memory browser opens on the right side, you just click on this area on the top and just give your memory value which you have used, or memory area. Like I have used 1800. So hex value 1800. I supply over there, and here you can see I had previously written the value of 5678 and 1234. Actually, the value was this one, hex value of 12345678, as because I have enabled the 32-bit mode. But this is a little endian processor, so it will store the 5678 in this particular byte and 1234 in the other part. So accordingly, the data will be adjusted, and this is the entire 32-bit data. So here we can just run the code. Maybe I can just change the value to 9 over here, and we download the code once again so that we can see that the value actually changes. Okay, so now what I would suggest you is that in line number 91, where I put the processor to a halt, just put a breakpoint and you run your code. And here you can see on the right side that your data is already written. So 12345679 is the value that was supplied. So like this, you can simply use it to store your own data. And never mind, like if I go back to the code and I show you that what is the map, how does the map file look like. So here you can easily see that your entire code is limited to the text region. So here it starts from 5C00 and of the length of 1C. That is the starting of the text area, and from there it jumps to another area which is over here. So this is the extended. So this is the initialization part. You can say this is the initialization part, the boot.c file, and that is our trap. And after that, this 0 hex value 10,000 is the memory, is the actual memory where your code is there. So just remember, if you're using the upper part of the flash, so just remember to place it above 10048 hex. So in that way, you will never crash with your existing flash or code. So all the best. Thank you and goodbye. And please do write in the comments if you have any particular question. And if you like this video and if it is helpful to you, please subscribe to my channel and do click on the bell icon, and that way you will come to know whenever I update a video. Thank you.